All right, good people. Welcome to video number 6. This is really the last video of this part 1 of anti-differentiation. We're practicing taking the antiderivatives of different functions. We're looking for the function whose derivative is the one we have. So, a couple of things to remember. Whenever you're integrating, remember we often need to rewrite or simplify the integrand before attempting to integrate. So, don't just jump into integration, right? Don't jump into the integration. You got to see, can we simplify the problem? Can we rewrite the problem in order to make it look nicer, in order to take an easier antiderivative? The bad news is we don't have product rules or quotient rules like we do in differentiation. So we need to simplify the integrand first before we head into taking the antiderivative. And always remember that an antiderivative is the reverse of a derivative. So use this in order to help you find an easier way to take an antiderivative. So we're going to take a look at some setups here that at the beginning might look a little like what, but you're going to find that maybe they're not as bad as you think they are. All right. So let's look at number 1. Or example 8a. We just said that taking the derivative or taking antiderivatives, we don't have a product rule. And that's exactly what we have here, a situation where we are multiplying two things. And so we're going to have to simplify this first. And that means let's multiply this out. So we have a binomial times a binomial. So we're going to multiply 3x times x. We're going to multiply 3x times 4. We're going to multiply minus 1 times x, and we're going to multiply minus 1 times 4 in order to make our integrand a little bit easier to work with. And then, of course, I can put these together in the middle here. If I have 12x's and I'm subtracting 1x, then I have 11x's. So I'm going to say this is plus 11x. Great. Now I'm going to use the properties of integrals and say I can split these up. I don't have to show that, and I'm not going to show that, but I guess the middle step would be something that looks like this. And then I can start taking antiderivatives of these independent terms. So the derivative of this would be x to the 3 divided by 3 plus the antiderivative of this would be x to the second divided by 2 minus the antiderivative of this would just be 4x plus c. I don't know why I put these equals over here. Also, I haven't really brought this up, but have you noticed that as soon as I take the antiderivative, I don't need this symbol anymore, the integral symbol. I don't need the dx anymore. Once I take the antiderivative, those are gone because they're telling me to do something, and as soon as I do it, well, then I don't need them. So my antiderivative here would be x to the third plus 11 halves x squared minus 4x plus c, and that's my antiderivative. But I couldn't have done that by taking the antiderivative the first times the antiderivative the second. No, I can't do that. Just like I can't take the derivative the first times the derivative the second. In derivatives, we have a special rule for that. In integrals, antidifferentiation, we don't have a special rule. So we need to rewrite it by multiplying everything out and then going from there. So you would have to do something similar for letter C, right? Like trying to figure out, excuse me, trying to figure out how to multiply this out. So I'm not going to finish letter C, but I'll certainly start it for you. If we're squaring this, remember that means we're multiplying 2x minus 3 times 2x minus 3. So that'd be 4x squared minus 6x minus 6x plus 9. And again, we can put the middle terms together. And so that's going to be minus 12x. And then I can take the antiderivative of that similar to the way I took the antiderivative of letter A. When I get to letter B over here, at the beginning, this looks really complicated, right? I go back and think, is there a way we can reverse this process? But remember, we're trying to simplify as much as we can the integrand so that I can take an antiderivative a little bit more easily. And I remember that secant x, the definition of secant x is that it is the reciprocal of cosine. So this is 1 over cosine x. And if I know that, that means I can reduce one of these cosines with this cosine, and I'm left with just cosine x, right? This will reduce with one of these two, because there's two of them, because I'm squaring them. So this one on the bottom will reduce with one. I'm left with one cosine. And now I can take the antiderivative of cosine x, which is sine x plus c. And I'm done. So I guess letters A, B, and C show us that there's a way to figure out the antiderivatives. It's just a matter of simplifying first. So that when I look at letter E, similarly, I would definitely encourage you to multiply this out first and then take the antiderivative of those individual pieces. But what I want to do is look at both D and F only because we have division and there is no quotient rule, but we're supposed to somehow simplify it. So I'm going to tackle letter F first. I notice that I'm only dividing by one term. And so if I'm dividing by one term, that means I can divide the first numerator term by that one term on the bottom, plus the second numerator term by that one thing on the bottom, minus the last numerator term by that one thing on the bottom, right? If I'm dividing by one thing, that means I'm dividing everybody by that one thing. And now I'm going to try to simplify this as best as I can. Well, that means this will go to the numerator and it'll be x squared times x to the 1/2 dx plus the next one would be 4x times x to the negative 1/2. My bad. These should be negative 1/2 powers dx minus, and then the last one's going to be 2 times x to the negative 1/2 dx. And so now our job is to try to simplify this as best as we can. And so when I do this, I'm going to combine the like terms here, and that's going to give me 3/2 dx, and then this is going to give me 4x to the 1/2 dx, and then the last one will give me 2x to the negative 1/2 dx. Okay, so let me pause here for us to recap what we just did. When you're dividing by one term, you divide everything in the numerator by that one term and basically break it up into little pieces. You can do that. And then try to combine them as best as you can. So I can move this to the top, it becomes x to the negative 1/2. And then when I put these two together, it becomes that. By the way, I have not, to this point, I have not done any antiderivatives. All I've done is combined them, simplified them, separated them, and try to do the best I can to make it an easy antiderivative to take. And so now I'm ready to take the antiderivative. The antiderivative of this would be add 1 to the exponent, divide by the new exponent, my bad, plus add 1 to the exponent, divide by the new exponent, minus add 1 to the exponent, divide by the new exponent, plus c. And that's going to leave me with 2/5 times the square root of x to the 5th plus 8/3 times the square root of x to the 3rd minus 4 square root of x plus c. And that would be my derivative for, or my antiderivative for letter F. I think letter H will be an easier breakup of terms because I'm dividing x squared by 4x squared, 3x by 4x squared, 7 by 4x squared, and that might be a little bit easier. but this one was definitely a bear to separate. And then also, and same thing with letter G. If you look at letter G, this one's really easy because it's 3x to the fourth divided by x. So this is going to cancel with one of those, and x squared divided by x. This is going to cancel with one of those, and 3 over x, and that's going to lead you to a natural log. These are the easy versions of the division. When I come back to letter D, this is a little bit harder because I don't have one term. So I can't, and I'm going to say this again, when I have more than one term that I'm dividing by, in my divisor, this is the divisor, I cannot separate them into pieces. So what I have to do is actually divide this out. And so the question is, what is x squared minus 4x minus 21 divided by x plus 3? So I'm going to take x plus 3, and I'm going to divide it, like actually do long division for this problem. All right, so we ask ourselves, what times x would give me x squared? Well, that would be x, right? X times x would give me x squared. But x times 3 would give me 3x. And then I'm supposed to subtract, subtract, subtract. Well, that's going to cancel this. And in here, that's going to leave me with negative 7x. And then this drops and gives me minus 21. And then I start the process again. What times x would give me negative 7x? Well, that would be negative 7. Negative 7 times x, that would give me negative 7x. And negative 7 times 3 would give me negative 21. And when I subtract, that's going to change the sign here. So I'll just do that. Instead of writing the subtraction, that'll change the sign, that'll change the sign. And that leaves me with 0. It doesn't have a remainder. So it turns out that when I do this division, this actually just leaves me x minus 7 dx. And then I can do the antiderivative, add 1 to the exponent, divide by the new exponent. This is a linear term plus c, and I have my antiderivative. But the whole deal was I had to do long division to actually divide this whole numerator by x plus 3 to see what would be my answer. And this turns out to be my answer. So the moral of the story is, because there isn't a division antiderivative rule, because there isn't a multiplication division rule, we have to do the division, we have to do the multiplication to simplify as much as we can, and then take the antiderivative. This will be the last video for this section. We'll come back next time and we'll talk about part 2.